So for petroleum production engineering, this is going to be an introductory aspect to it. When you start the course, you will be looking at a few definitions, and they are quite basic and straightforward, so we'll not need to spend too much time here. So you first talk about what petroleum or crude oil is, and it's just a naturally occurring liquid composed of several organic components. The other thing we're talking about is the origin of petroleum. So there are two schools of thought. The first school of thought says that petroleum is coming from organic matter that's deposited over time and subjected to high conditions of temperature and pressure. And then the other school of thought says that petroleum actually comes from inorganic reactions. And these reactions are also occurring under conditions of high temperatures and pressures. So that's just something to keep in mind. Now, there's something we need to know. That's the definition of a source rock. So a source rock is a rock from which we can obtain petroleum in sufficient quantities. And so hydrocarbons are formed in these rocks and they can move from these rocks to locations of lower pressures. When this happens, we have what we call migration. So migration is just the movement of petroleum, and there are two main kinds of migration that we'll be talking about. So what we need to know over here is that we have what we call source rocks. These are rocks from which we can source petroleum or source hydrocarbons. And these hydrocarbons move from the rocks in which they are formed into locations of lower pressures. And these locations usually are what we call reservoirs. So we'll define reservoirs, we'll define migration, we'll talk about all these things. So when we talk about a reservoir, we're talking about a structure, a subsurface structure, a structure below the earth's surface, where we have hydrocarbons being accumulated and stored. The reservoir itself is permeable and porous, so it can allow fluid to move into it and all of that from the source rock. But then it has an impermeable layer surrounding it as well. So the reservoir where the fluid is being stored is permeable. Fluid can move there. But then it has this outer casing, which is an impermeable rock layer. So that's just something to keep in mind. Then now we're looking at migration. For migration, we have two forms of migration. There's primary and then there's secondary. So for primary migration, we're looking at the movement of hydrocarbons from the source rock into the reservoir. From the source rock into the reservoir. And in this case, the main mechanism behind the movement of the hydrocarbons is the difference in pressures and how compact the media we are working with are. Right, so the compaction is actually a result of the pressure differences. So we can majorly classify the movement of hydrocarbons under primary migration as based on pressure differences. So we have the source rock at a higher pressure and then the reservoir at a lower pressure. Hydrocarbons will move from the source rock into the reservoir because of the pressure differences. We also have secondary migration. And for secondary migration, we are looking at the movement of hydrocarbons from areas that are close to the source rock, and the hydrocarbons are moving into the reservoir. For secondary migration, the main mechanism of their movement has to do with capillarity and then difference in density, not pressure, as we saw with the primary migration. So with primary migration, the movement can be lateral, that's sideways. It can be vertical, that's both upwards or downwards. But then with secondary migration, because you're dealing with capillarity, the movement is only upward vertically. So this is the major difference between the two of them. For both primary and secondary migration, we are looking at the movement of hydrocarbons into the reservoir. But with primary migration, the movement can be lateral, that's sideways, can be vertically upwards or vertically downwards, because it's based mainly on pressure differences. But for secondary migration, because the main thing it is based on is capillarity, it can only move upward vertically. Okay. Now the main part of the introduction is what we are coming to talk about right now. So we're looking at the characteristics of reservoirs. One of the main characteristics of reservoirs is the porosity. And the porosity is just a ratio of the volume of pores to the total volume or the bulk volume. So this is the symbol we use for the porosity, the phi, and it's equal to the volume of the pores, which we've labeled as Vp, divided by the bulk volume or the total volume, which are labeling as Vb or Vt, right? So that's the bulk volume or the total apparent volume of the rock. And this is just the general equation for porosity. When we talk about porosity, we have two forms. We have the effective and the residual. For the effective porosity, we are talking about the fraction of pores that are connected to each other or connected to other formations in a way that we can have hydrocarbons and fluids being transmitted from them and to them. So we would have a diagram to depict this better. For residual porosity, we are talking about the fraction of pores that are isolated, they are closed, they are not open to other formations or other pores. So we don't have fluid flowing to them or from them. We may have fluid present in them, but the fluid in them is trapped. They are not able to flow out of them. We also will not be able to have fluid flowing into them because they are closed or isolated. So this is what we are talking about. At this part of the image here, we see that there are no pores here. So the porosity here is literally zero. It's very small. Over here, what we see is residual porosity because we realize that for a portion like this side is close to other formations or other pores. So we can't have fluid flowing into or out of this portion. But for effective porosity, so what we have at a point like this, over here we see that if there's fluid at this point here, it can easily flow to other portions. So this is what we call effective porosity, and this is what is actually of interest to us in this course because we want to see how much fluid will be able to flow within a particular structure we are given. So effective porosity, we said, is the fraction of pores that are connected to each other or connected to other formations in a way that fluid can be transmitted to them and from them. But residual porosity is the fraction of pores that are isolated or they are closed. Fluid can't flow to them and fluid can't flow from them. Now, the total porosity, we can calculate it as the sum of the effective and residual porosities. And one important thing to note is that porosity, sorry, supposed to be decreases. Porosity would decrease with increasing depth because as we are increasing pressure, we are going to reduce the overall porosity. When we increase the pressure of the structure, we are making it more compact. We are pushing the structure together. And so the amount of space that's available, the amount of pore space that's available will reduce. So it was supposed to be porosity decreases with increasing depth. Okay. Now, another property we look at for reservoirs is the compressibility. And reservoir rocks are compressible. So we can calculate the compressibility for the overall rock sample or the compressibility considering just the pores. If you're looking at the rock sample, then we are looking at the change in the volume of the sample when pressure changes. That's what compressibility is about. So for compressibility, if we are applying pressure to a sample, how much does its volume change? That's what we are looking at. We're looking at the change in the total volume of the rock sample as pressure is changing. And we are doing this with respect to the total volume or as per the total volume or per unit volume of what we are working with. So this is our first equation. This is the compressibility of the rock sample. We can do this considering just the pores, so the porosity based on just the presence of the pores. So for this one, we are looking at the change in the volume of the pores as pressure changes. And that's going to give us the compressibility of the pores. The reason why we are doing this is because when we are dealing with the reservoir, we have what we call the solid matrix or the solid aspects of the reservoir, and we have the pores. The solid part is the part consisting of the rock material itself. So when we apply pressure to such a structure, we can have the solid part, that's the solid matrix, being compressed. And we can also have the pore spaces being compressed or being reduced as we apply pressure. So we can do the porosity, so we can check the compressibility for the solid matrix, and we can check the compressibility for just the pores. If you are considering it for just the pores, then it becomes this formula where the compressibility of the pores is given by this. And as I said, we are looking at the change in the volume of the pores with respect to with respect to the change in pressure being applied. And we are doing this per the total volume of the pores so that we can determine the compressibility of the system. Now, remember over here, we said the compressibility of the entire rock sample was given by the change in the total volume. In this case now, we are expressing that even further, where the total volume is now being expressed as the volume of the solid matrix and the volume of the pores together. So we want to look at the change in the volume of the solid matrix and the change in the volume of the pores when we are changing pressure. So that's just the difference between equation 1 and equation 3. It's the same thing, but then this time we are expressing the total volume as that of the volume of the solid matrix and then the volume of the pores. In the case where the solid matrix is not so compressible or the compressibility is negligible compared to that of the pores, we can take the first part, this part here, the change in Vs over change in P, to be approaching zero or to be zero. We are taking it to be negligible. So our equation 3 can now be simplified to equation 4, where we have the compressibility of the rock or the compressibility of the rock sample in a reservoir to be dependent on just the change in the volume of the pores with respect to the change in pressure. And this is because, as I said, it's possible that the particular material the rock is made of is not so compressible, or the compressibility of that solid matrix is very, very small compared to that of the pores. So in that case, it can be neglected, and we have the compressibility of the rock to be this. Now, if you want to compare the compressibility of just the pores to the compressibility of the entire rock sample, right? We can divide equation 2 and equation 4. So this was equation 2, the compressibility of just the pores, considering the volume of the pores, right? So we divided it by the total volume of pores, so as per volume of pores. For this one, we divided it by the total volume of the entire rock sample, so as per the volume of the entire rock sample. If we divide the two, we can have Cp divided by Cr to give us Vt over Vp. So as we said, it's just equation 2 divided by equation 4, and we see that del Vp del P is the same for both of them, so they cancel out, so that we end up with Cp over Cr to be equal to Vt over Vp. Now remember that for porosity, we said that it's equal to the volume of pores over the total volume. And from equation 5, we said Cp over Cr is Vt over Vp. So this expression here is the same as 1 over porosity. We said porosity was Vp over Vt. So that's what we are going to have here. Cp over Cr becomes 1 over the porosity. And we can see that Cp is equal to 1 over the porosity times Cr. So we were saying that for Cr, right, once again, in this situation, we're saying that the compressibility of the solid matrix is very negligible, but we are doing this as per the total volume, not as per the volume of just the pores. So that's the difference between the Cr and the Cp. And when we divide the two of them, we end up with equation 6, which we would use later on. The other thing that we can talk about is the permeability. So when we are talking about permeability, we are talking about the property of the rock sample to allow fluid to flow through it. And permeability is calculated using Darcy's law. So we relate the rate of discharge, or the rate of flow through the medium, to the viscosity of the fluid, and then the pressure drop over a given distance. A fluid that is highly viscous will not be able to flow properly. And then a system where there's a large pressure drop, right, would have more fluid being discharged, yes, per time. So we have here our Q over, so that's the Q is the flow, relating to the flow over the area, right? And this is the surface area. K is the permeability constant. Then the dp dx is our hydraulic pressure gradient. So it's just a change in pressure with respect to change in distance. And then the mu is our viscosity. When we are working with reservoirs, usually assume that they are cylindrical in nature. So the expression becomes this. So we'll do the proof for that very soon. Yes, we'll do the proof for this very soon. So, um, okay, okay. So for this one, remember we said we have Q over A to be equal to KdP over mu dx. If we are dealing with the cylindrical flow, or in fact, before we do that, our Q is going to be equal to AK over mu, then dp over dx, or del p del x, dp over dx. So our area is going to be given by 2 pi h, 2 pi rh. Sorry, so let me bring the r here. And the assumption is that, um, oh, sorry. The assumption is that our reservoir is cylindrical in nature. So we have the reservoir to be this way. Okay. And then we have the radius, and then we have the height here. So if you want to find the surface area here for just this portion here, it's going to be 2 pi rh. That's going to be the area that we are working with. So that's what we'll put in here. And instead of dx, because we're dealing with something cylindrical now, we are going to look at the change in the radius. So what we are going to have is 2 pi RHK over mu, and then dp dr to be equal to our Q. Now what we can do is that, okay, we can simplify, or we can arrange our terms here, because we don't want the r to be a denominator here. So we can send r to the other side of the expression. So we have k over r times the r to be equal to 2 pi h k over mu, then dp. Then we can integrate both sides. So for this one, we're integrating from p1 to p2, and here from r1 to r2. So if we do this, what we are going to get is, let me clean this side. If we should do the integration, what we are going to have is, we'll have Q ln R2 over R1 being equal to 2 pi hk P2 minus P1 all over mu. And we can make Q the subject and have 2 pi hk P2 minus P1 all over mu, then ln R2 over R1. So this is what we are going to have. Now, with the when we are dealing with our reservoir, right, our R2 is going to be the radius of the entire reservoir. So from the center here to the end of the reservoir. And our R1 is going to be the radius of the well bore. So the well bore is just the portion that we are drilling into the reservoir. Right, so that's just going to be the radius of the well, because we're going to have fluid flowing from the reservoir into the well bore. So it's going to be our R2 is going to be the radius of the reservoir, and then our R1 is going to be the radius of the well bore. So we see over here that we have capital R over RW. The capital R is the radius of the reservoir, and then the RW is the radius of the well bore. So that's that's the proof for that formula.